Let's try to design the circuit for simple mathematical operations such as addition, subtraction on single bit using digital circuits. So in case of single bit addition, suppose the two bits are A and B, and it will generate sum and it will generate carry. So if we try to understand, then 0 plus 0, the sum is 0, let us write sum here, and carry here, the carry will be 0. When it is 0 plus 1, the sum will be 1, the carry will be 0. When it is 1 plus 0, the sum will be 1, carry is 0. And when it is 1 plus 1, the sum will be 0 and carry will be 1. So let's from this draw the truth table of this. So 0, 0, 0, 1, 1, 0 and 1, 1. Then we get sum as 0, 1, 1, 0 and carry as 0, 0, 0 and 1. If we observe the truth table, then we immediately understand that this sum is nothing but the XOR gate and carry is nothing but the AND gate. By observing this we understand, but otherwise the method of finding of minterm. So this minterm is A bar B bar. This minterm is A bar B. This is A B bar and this is A B. Then if you see the sum is equal to, sum is 1 for this and this case. So that is equal to A bar B plus A B bar, which is nothing but XOR gate A XOR B. And if you consider the carry, then carry is equal to 1 only for this case. So that is A dot B. So that is AND gate. So here we have to use XOR gate and here we have to use AND gate. So with one XOR gate and one AND gate we can design the circuit. So this is the XOR gate. This is the AND gate. Both are having the inputs A and B. So this is A input. This A input is connected to XOR gate as well as AND gate. B input is also connected to XOR gate as well as to AND gate. Then XOR gate output will generate sum and AND gate output will generate carry. This becomes the circuit which is known as half adder because it adders only 2 bits. And its block diagram is shown in this form, that this is a half adder. It has 2 inputs A and B and it has 2 outputs sum and carry. This is known as half adder. Similarly, if we want to subtract the 2 bits, then in case of subtraction, suppose we want to subtract A minus B, then A will have the value 0, 1, B will have the value 0, 1, and the subtraction what we want is A minus B. In case of subtraction, the sequence is important, that B is subtracted from A, which is not important in case of sum. So when A and B are there, they will have 0, 0, 0, 1, 1, 0 and 1, 1, and then it will generate the answer of subtraction and it will generate the borrow also. So let us see, 0 minus 0 is naturally the subtraction is 0 and borrow is also 0. If we consider 1 minus 0, then answer is 1, subtraction answer is 1, the borrow is 0. When it is 1 minus 1, it is very easy, the answer is 0, borrow is also 0. But the case is that 0 minus 1, 0 is smaller than 1, so borrow is taken from this side. 0 minus, so when borrow is taken, this number becomes 1, 0 and 1, 0 minus 1 is 1, so the answer is 1. So from this we can draw the truth table as, when it is 0, 0, subtraction is 0, borrow is 0. 0, 1, this is the case. 0, 1, this is the case. When subtraction is 1, borrow is also 1. 1, 0, subtraction is 1, borrow is 0. And 1, 1, both are 0. Again, if you observe, you can immediately see that this is the XOR gate and this does not directly match with any of the gate. So let's find out the minterm where 1 is there. This minterm is A bar B, where the borrow is 1. So again we can write that subtraction is equal to A bar B plus AB bar, which is nothing but XOR gate, and borrow is equal to A bar B. Borrow is A bar B. So let's draw the circuit diagram for this. It will again need one XOR gate to generate sum, one AND gate to generate borrow, not sum, subtraction. This will generate subtraction, sub, and this will generate borrow. This will have the input A and B. A and B are the inputs for generating subtraction. For borrow, the inputs are A bar and B. So B is taken as it is here, but A is taken through inverter. So it will become A bar. So A bar and B, this will become A bar dot B, that is a borrow. And here A XOR B, that is subtraction. So this forms the half subtractor. Half subtractor. It has inputs A and B, and it has output, subtraction output and borrow output. Now these two methods of addition and subtraction were for single bit, but practically multi-bit additions and multi-bit subtractions are done. So when multi-bit addition is there, for example, let us consider 1010 plus 0111 for example. Then 0 plus 1 is 1 because there is no any carry coming from behind. 1 plus 1 is 0. 1 plus 1 is 0 and carry 1. 0 plus 1 plus behind carry. So 1 plus 1 is again 0. This 1 plus 1 is again 0. And this is the one which is the ultimate carry. This is the example. We'll have one more example if you want. So suppose 1011 plus 100. Suppose these two numbers we add. One bigger number, double carry actually I want. So let us change this number to 0 1 1. 1 plus 1 is 0. Okay, this number is coming same. So suppose 0 0 1. So 1 plus 1 is 0 and carry 1. Now let us see here, this is added, this is added, this is also added. So 1 plus 1 is 1 0, 1 0 plus 1 is 1 1, so 1 1 will be added. Now here the addition will be 1 with there is no carry, and here the addition will be 1. So this is the method. Now let us consider that this number is a number, then this becomes A3, this becomes A2, this becomes A1 and this becomes A0. Similarly this is B number. So if we consider here, then A3 plus A2 plus A1 plus A0 will be added to B3, B2, B1 and B0. This becomes the addition of 4 bit. When A0 and B0 are added, there is no carry from behind. So this will generate the addition S0 and carry C0. This C0 carry has to be added with A1, B1 and C0. It will generate S1 and carry C1. This will generate sum S2 and carry C2. This will be added to generate sum S3 and carry C3. And the ultimate answer will be C3, S3, S2, S1, S0 is the addition. So in this case, you can see that only for this addition we can use half adder. If we want to add, then half adder is not sufficient because it is actually adding 3 bits. So for that we need full adder. So full adder has a block diagram that it adds A for any case. Suppose A1, then n is equal to 1. So An when it is, Bn when it is, then it is adding Cn minus 1 because A1 B1 and C0, A2 B2 and C1 because it is coming from behind, and it will generate the output Sn and Cn which is to be used next. So this becomes the block diagram of full adder. Now let us design the circuit for full adder because full adder is adding 3 bits simultaneously. Now when the 3 bits are added for full adder, let us have the truth table of this. So A, B, C, then there will be carry and there will be sum and carry, sum and carry. So there will be 8 combinations: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 100, 101, 110 and 111. Now 0 plus 0 plus 0, naturally sum is 0, carry is 0. In all the cases where there is a single one, sum is 1 and carry 0. Sum is 1 and carry 0. Here also sum is 1 and carry 0. Whenever there are two ones, 1 plus 1 is 0. So sum is 0 and carry 1. Sum is 0 and carry 1. Here also sum is 0 and carry 1. When three ones are added, 1 plus 1 is 1, 0, plus 1 is 1, 1. So sum is 1 and carry is also 1. So this becomes the truth table of full adder. Now from that we can write down the equations for sum. For sum is 1 for this and this case. Now we know the minterms a bar, b bar, c bar. Here a bar, b bar, c. This will be a bar, b, c bar plus a bar, b, c. Then here a, b bar, c bar. Here a, b bar, c, a, b, c bar and a, b, c. So let's add all the minterms which are generating output 1. So we will take this. For sum, we will take the values as a bar, b bar and c plus next value a bar, b, c bar plus next a, b bar, c bar plus a, b, c. This is the equation for sum. From the sum equation, we can take suppose a bar common here. Then a bar becomes b bar c plus b c bar. And when you take a common from this, we get b bar c bar and b c. We have already studied that this is for XOR gate of b and c. This is for XNOR gate of b and c. So this will be, suppose let us consider this is k and this is k bar, then you immediately understand that a bar k and a k bar is nothing but a XOR k. But k is nothing but b XOR c. So ultimately this becomes a XOR b XOR c. This becomes the equation for sum. Now let's do it for carry also. For carry, let us sum all the terms, this and this term. So this is a bar bc plus a b bar c plus a b c bar plus abc. Now we know that a plus a is equal to a. So whenever a term is there, we can write down a plus a plus a. So let us add to this equation as plus abc one more plus abc one more, because it will not change the value overall. Now let us combine this and this together. So what we get is a bar bc and abc. So bc is common, a plus a bar. Now take this term and this term together, where you can take ac where b plus b bar. Now take this term and this term together, where we get ab c plus c bar. Now a plus a bar is 1, b plus b bar is 1, c plus c bar is 1. So ultimate equation becomes bc plus ac plus ab. This becomes the equation for full adder carry. Once we got the equation, let us draw the circuit for this. For full adder, we have got the equation as sum is equal to a XOR b XOR c and carry is equal to ac plus bc plus ab. So let us draw the equation, draw the circuit diagram. This is a, this is b and this is c. Then there will be an XOR gate which will generate sum, which is equal to a XOR b XOR c. So a will be one of the input, b will be another input, c will be the third input for this. Then there will be 3 AND gates, 1, 2 and 3, and all are together connected to one OR gate that will generate the carry. So this will have input AB, this will have input BC, this will have input AC. So for this, let us connect the inputs. So A will be connected to this, as well as A will be connected as an input to this. B will be connected to this, as well as B is connected to this. C is connected to this, as well as C is connected to this. Now this becomes the complete circuit diagram of full adder. One more thing we can understand, we know one half adder. So by combining two half adders together, suppose this is one half adder, this half adder will add A and B and generate a carry and sum. Then these two bits can be added together with another half adder that this adder has. This will be the sum, and the C, this is AN, BN and CN minus 1. It will add the two. It will generate a sum and it will generate a carry. The carry will be generated either from this half adder or from this adder. So this will generate ultimate carry and this will generate ultimate sum. This is another way of designing full adder. In this case, the circuit will be such this. This first XOR gate will have the inputs A and B and it will generate a sum. There will be one AND gate which will have A and B as the input. It will generate the carry. There will be another half adder which will have one XOR gate. This XOR gate will have another input is sum C, and this sum will be used as another input for this. So this circuit will generate ultimate sum. The same two inputs are given to this AND gate for second half adder. This will generate one carry. This is generating another carry. These two carries are combined to form the carry of the full adder. So this is another way of designing full adder using two half adders. So as full adder does addition of single bit in multi-bit addition, if we want to do this type of 4-bit addition, then in this case for every addition one full adder will be implemented. So 4 full adders are implemented. In case of first full adder, A0 and B0 are added. As there is no carry from behind, the carry is connected to 0, it will generate a sum. Then the carry generated from the addition of the rightmost bit will be added in the next. So A1 and B1 will be added with C0 to generate S1. Then it will generate a C1. A2 and B2 will be added with C1 to generate S2, and A3 and B3 are added to C2 to generate S3 and C3. This becomes the complete circuit for 4-bit addition.